In the previous video, we looked at the geometric interpretation of vectors. And as it turns out, matrices have a geometric interpretation as well. Vectors represent points in space, in n-dimensional space. Matrices, these guys represent functions which go from one-dimensional space to another dimensional space. So let's take an example. Suppose I have the vector space of the entire plane, because this is a vector space. Take any two vectors in the plane. When you add them together, you'll get another vector in the plane. So as it turns out, the entire plane, which is the set that we often refer to as R2, the set of all vectors x1, x2, such that x1 and x2 are in the real numbers. The question is, can I take any point and convert that into a point in a different dimension or even the same dimension? And the answer is yes. So here's the idea. I want to take these points and basically, suppose I just want to drop them down to the real number line. In other words, I want to take any point here and correspond it to another point on the real number line. Put differently, I want to define a function between the plane and a line. The question is, how do I do that? As it turns out, you can do this with a matrix. So here's what you do. Recall what we said. If we have an M1 by N1 matrix, and we multiply that with another matrix, we need the other matrix to be, and I'm just going to get rid of the 1 here. And we need the other matrix to be to have the inner ones here the same. Okay, well, suppose that I have a vector. This is a vector, okay, where it's a column vector, in which case I'll have an n by 1. Okay. Suppose that I want to convert this vector, which is in n dimensions, I want to convert it to a vector that's in m1 dimensions. So in our little example, we went from 2 dimensions to 1 dimension. In which case, what we're going to do is we're going to have a 2 here. I'm so sorry. No. We're going to have a 2 here, and we're going to have a 1 here. And the... No, I'm sorry, I screwed that up. Again, this is still 1. This is 2. Inner one is here is 2. Okay, so to convert from a 2-dimensional to a 1-dimensional, I need a matrix. I need a 1 by 2 matrix, which is a row vector, right? So suppose then that I define this matrix A as, let's say, 3, 4. Then, as it turns out, if I take any vector x in R2, I'm going to use here to emphasize it's a vector. This is equal to x1, x2, right? Then when I multiply that by A, what I'm going to get is a number. So A is effectively acting as a function, bringing down points in 2-dimensional space to points in 1-dimensional space. Why is that? Do the multiplication. We have 3, 4 multiplied by x1, x2. We recognize this as a dot product, and so this is the same as 3x1 plus 4x2. So if you're if you give me a vector, I can give you a point that is on a line. So what have I done? I have effectively converted points in two-dimensional space to points in one-dimensional space. I've reduced the dimensions down. Let's take another example. Suppose I have points in three-dimensional space, and I want to reduce them down to points in two-dimensional space. We know the way to do that is by multiplying it by some matrix. So we know that points in two-dimensional space, let's see, we have three-dimensional space, okay, x1, x2, and x3. And we multiply that by some matrix, and we want to get out points in two-dimensional space. And to avoid confusion, I'm going to use the notation y1, y2. So how do I do this? Well, if this is a 2 by 1 and this is a 3 by 1, to get the 2 by 1, I need a matrix that is 2 by 3, right? Now, depending on what that matrix looks like, that matrix is going to do different things to the points. So each matrix defines a unique function between three-dimensional and two-dimensional space in this instance. So let's suppose that we use something that kind of looks like the identity function or a matrix. I say kind of because it's not exactly the identity matrix, because we would need a third row for that to be true. But let's just use that. And when we multiply those two together, we get an equation to use for y1 and y2. For the first one, we get this multiplied this, x1 plus 0 plus 0. And then for the second one, we get x2 plus 0 plus 0. And we just get x1, x2. So this is often what's called a projection function. The reason is that all we're doing is just, given this point is in three-dimensional space, we went this long and this out and so on and so forth. What we're doing is just saying, forget the third dimension. Look at the point in this XY plane here, if you can see that. And here's the points that we're going to be looking at, where this is x2 and this is x1. Now, the matrix could have done something different. We didn't need to do this. We could have come up with something else, something like 1, 1, 1, 1, 1, 1. And we would have x1, x2, x3. In which case, the function that converts my three-dimensional vectors into two-dimensional vectors looks something like this. It looks like x1 plus x2 plus x3, right? This times this, plus this times this, plus this times this, and the same thing. Which, by the way, is just described by any number x. Well, I don't want to get into that, but okay, you get the point. This is just x1 plus x2 plus x3. Okay, I can simplify that down further. So the way that I can, but I get a nice neat equation here for both dimensions individually. Either way, the point is that we can view matrices as functions which convert vectors from the, notice this is a 2 by 3 and this is a 3 by 1. So we can view matrices as functions which convert vectors of the number of columns here that I have to other vectors which are in the first number of rows here. So for any n by m matrix, the way we can think of a matrix is as a function from m-dimensional space to n-dimensional space. What if n and m are equal? Then as it turns out, the matrices look like very fascinating functions that can act as rotations, expansions of the plane, contractions of the planes, symmetries, and other geometrical interpretations. Is a little outside the scope of our discussion. The primary thing you should just know, although I'm not really going to hold you to it on this aspect of our discussion, but the one thing that you should recognize is that vectors act as points in space, matrices act as functions which map n-dimensional spaces to higher or lower dimensional spaces. So hopefully you understand this concept.